In the very last video, it's a little kind of context question, 2 marks. It's more about visualizing it than anything. So we've got our cost graph, and the shaded part here is 1/2. So I know that is 1/2. Okay, and it wants to know what is the value of this. What does that mean? If I integrate this function, which is the function we've got, between 3 pi over 4 and 0, I am going to be looking at the area here and the area here. I just thought it was an interesting question because it does make you think. So how could I possibly work out this? I need to know that without any real information. Well, don't forget the sine waves and cos waves are symmetrical. So with these waves, if you've got, doesn't matter if it's sine or cos, this area here equals this area here. And if you look, they've actually cut the wave, haven't they? Just kind of at the halfway point. So that should carry on over here like this. Okay, so I've got half of a wave is a half. So this in here would be equal to 2/2. Yeah. This part here is the same as that, and that's the same as that. So the whole thing is going to be equal to 1, but it's below the axis. So the area there is -1. So when I'm doing this, I'll say, well, the full area then, if I was to integrate that, and usually we integrate it between the axes so that I can then make a sensible decision. Like in reality, the area here is a half plus 1, so the area is 3/2. But if I was to integrate it like this, where I've got a limit here and a limit here, that my calculation would show this as being -1 plus a half. So the answer is -1/2. And that's why we only integrate between the points on the axis, because that doesn't really make sense, does it? If I want to know the area of this and this, it's 3/2, it's a half, and then it's this 1. So the whole thing really is 3/2, but below the axis comes out as negative, which is why in this case the number you would get from this kind of almost an erroneous calculation, would come out as -1/2. So I quite like that question, just to make you think that, to remind you of the symmetry of the sine and cos waves, and just to remind you what you're doing when you integrate as well. Okay, so when we integrate, we usually just go between the points, and then we would say, right, that area is -1, but I'm going to call it 1 because you can't have a negative area. The negative just indicates it's below the axis. And yeah, that is us finished. I did one extra little question. I've not seen it come up before. It's this one here. I'm not going to talk through it too much. There's a missing integral. So just to kind of show you what I did, I started off by, so what it says is the integral between a and an unknown in this, so that integral equals a half, i.e. the area under the curve between a and this is a half. So what it's looking for you to do is to integrate. Okay, so integrate sine, get negative cos, that's fine, divide by differential, okay, and I've got a and pi over 8. And then you say, okay, well, substitute a in, so I've got this kind of unknown, but I can put pi over 8 in here, and that works down to an actual fraction. That's great. And then you start rearranging. Take your, you know that this integral equals a half because it said that the area is a half. And then all you're doing, move your quarter over and move your 4 over. So times, so take away a quarter and divide by 4. So I know I've got negative cos is 1. Well, let's times both sides by -1. So I've got cos of my function is -1. When is cos equal to -1? At 180 degrees or at pi. So I know that this has to be equal to pi. And then just rearrange it to make a the subject. Move your pi over 2 over and divide by 4. Okay, so I was going to do a separate video on that, but I thought, I'll just leave it there. You could try that yourself if you want. I've not seen many of those pop up actually, but it's just a slightly different way of making you think, really. But it's all the same things that we've been doing. And again, I suppose the thing I quite like about it is the rearranging aspect, especially when we get to here. Times them by the -1. And then saying, okay, well, when is cos -1? It's just visualizing the graphs. Quite like that. And then it's just a little bit of standard change of subject. So that was a 6 marker actually. So I'm guessing that would be a kind of towards the end maybe of an older paper. But yeah, I've got that there for you so you can see the working. Pause the video. Feel free if you want to give that one a little try. And just to then recap, we'll see if I can zoom right out. Right out, there we go. We have done differentiating composite functions, integrating composite functions. We have done differentiating trig and integrating trig, and then there was a little context question. If you can do all these, I think that's most of the types of questions covered. Remember, when you're doing these, inside the brackets staying the same. When you're differentiating, whether it's trig or whatever, you are timesing by the differential. When you're integrating, you're dividing by the differential. You do not have to remember this because you are given this at the front of your sheet, which reminds you when you integrate, you're dividing by the differential. When you differentiate, you are timesing by that. That's obviously for trig, but that applies for our regular functions as well. Okay. The other thing I would suggest you do, like I'm doing here, write down something you know, like what's differentiating again? Oh yeah, I times these two together, the coefficient and the power, and take one away from the power. Remind yourself of that. Same when you're integrating. What do I do again? I add one and divide by the new power. Okay, so just try and not get confused between the two for a start. Remember your dx's, remember your c's, and yeah, you're dividing by the differential for integration, timesing by differential for differentiating, and dividing by differential for integrating. So yeah, that's the end of this series. I hope that's been helpful, and yeah, have a wee go at that trickier question if you want there, where you're trying to find the limits. There's more examples like that in Zeta as well, if you want to challenge yourself. Yeah, best of luck. Thanks.